1.
Today's SparkFun Live. I'm Casey.
And I'm Evan.
Today we're going to be building a temperature sensing lunchbox.
So the principle of the operation for the temperature sensing lunchbox is it takes a reading from the analog TMP36 sensor, processes it via analog input to the Arduino Pro Mini, and then outputs that post-processed result as an LED along the 30 LED bar graph display. The wish list and the models, as well as the code, are going to be available on the GitHub repo, and
the wish list is in the description, as long as the code for the GitHub. So,
all right,
let's go for it.
So I think first thing to do is just jump right in. So with most of our kits, the key is, especially with the through-hole kits, is to start with the lowest profile components first. I suppose the zeroth rule is to actually make sure that your soldering iron is on and that all your tools are at hand. So I'll start with the 1K ohm resistor, and then I'll dump out some of these capacitors, the 0.1 microfarad filtering capacitors. And as a general practice, there's not really an official up or down on these boards, so I like to make sure that all of my like components are facing the same direction. So I've got these 4 capacitors to just get populated here. Before I get too far, I'm actually going to come back and get these tacked down.
So it's kind of nice to have a temperature sensing lunchbox. Say if you bring something like a macaroni salad and you leave it in the car, and you have something you just don't want to go bad. So it's kind of nice that as the temperature rises, you'll see the little bar graph will eventually rise to the top, and it kind of opens up the possibilities of, you know, understanding like, when does food go bad. So I know that a lot of refrigerator companies and appliance manufacturers are actually looking into these problems and trying to solve them in various ways, whether through RFID or, you know, other sensing methods. So it's kind of an interesting way. Jazz up your lunchbox, take it, show it off to your friends, and
be the coolest nerd on the block.
Be the coolest nerd on the block.
So I'm just laying down my my tack solders for the small discrete components now.
Now, Evan, you were once in production downstairs, right?
That's right, I was.
That's why you rock at this.
Well, just don't let the production boss Adam see these joints that I'm putting together, because they are, by his standards, very sloppy. However, I'm just looking for not having solder bridges and not having cold joints, so these will be just fine. Not sending this guy up into space this time. Maybe on the next revision. So at this point, now that I've got the first 5 components on, I'm just going to trim the leads so I've got some space to work. And then, so that's clear. I'm going to jump to the 330 ohm resistor buses.
I'll borrow one of these, get a shot.
Sure. Now these things are great because they link 5 330 ohm resistors all in a single small package with only one ground line to have to contend with.
So is that ground line marked on these resistors?
On the resistors,
let me flip over to a side.
Let's see. I think that might be the dot indicator.
Okay.
On the text. And cool. So when polarity doesn't particularly matter, it's just nice to have all your parts facing the same direction. But when polarity does matter, it's especially nice to have them, you know, work.
Excellent. So you may see some of these, some robots floating around. This week is National Robotics Week, so we want to give a shout out to all of our first teams that are out doing regionals, and there's several robotics events across the country, of which I'll be attending one this weekend in Ohio. This weekend there's some events in the local area, but it's Robotics Week. Have you hugged your robot?
I know I have. But just for the record, come here, you.
Touching. So.
No.
So
Yes.
feel free, while Evan is feverishly working, feel free to comment. I'm going to try and monitor these and answer any questions you have. Answer questions about this or SparkFun in general or life in general. Well, anything.
And can't forget that last one. So right now I've got these in, and I'm only putting down one solder joint, and that will allow me. It's a lot easier to take out one than 6 or several, so I can get them at least mounted in place, and you can see that they're not very straight. Then I can come back here with the iron and just sort of reflow that and get the proper alignment.
Now, how critical is the alignment of these components?
On the resistors, it's not terribly critical. There's a good, well, the ones that are closer to the LED display are going to be, if they lean forward too far, they will actually interfere with the mounting. So I want to make sure to make a nice wide avenue that'll allow the LED boxes to go in unfettered.
Nice.
And so last time on SparkFun Live, one of the engineers, Mike, was touting the greatness of using leaded solder, which is I find is immensely helpful, especially if you're not into using a lot of flux. There is the added risk, but it's just generally a nicer quality joint. Mm-hmm.
Is that because of the melting temperature, or do you think some of the chemistry is involved?
I think it's got a lot to do with the melting temperature, but moreover, I think the chemistry involved in the lead-free is not much better as far as health hazards go. So it's the benefit's sort of a wash, I think. Mm. But if you're into making sure that you're RoHS compliant, you definitely got to go with the lead-free stuff. Since this is just a simple project, I'm not too terribly worried about having a little bit of lead on my fingers. I'll just make sure to wash my hands before the next time I eat.
So we got a quick question from Joshua Deco. Casey, if you put your jet engine in the lunchbox and turn it on, what temperature would it be? Very hot. So the engine runs at about 600 C on the exhaust, so it'd probably melt the box.
And it's definitely outside of the reading level for the sensor itself.
Yeah. Let's. I'll take a look and see what our actual.
Just call up the data sheet there.
Yeah. Let's see what the ranges are of this temperature sensor.
All right. So I've got the bus resistors on. So I think the next critical component would be the ICs. The electrolytic capacitor is just a slightly bit taller. So make sure to get these down. Actually, I might have wanted to get them in before mounting the resistor buses, but it's not, order of operations here is not critical, it's just helpful.
So I noticed you kind of folded the pins over a little bit before you're inserting them?
Absolutely, Casey, and the reason for that is when these things come out of the tube from the factory, they've got a nice wide angle there, if you can show our viewers that.
See if that's a little.
Now we tend to draw these draw the hole patterns off of off of a more parallel-legged pitch. So and that's generally true among ICs. So in order to get them to fit most easily, and you can see I'm having a little bit of, there we go, a little bit of fun trying to get that in there. So that's sitting pretty and ready for the next IC. So these are the 74 NC595N shift register, also a popular circuit in our SIK. Now these are great for taking a few digital outputs, well, 3 digital outputs, and turning them into many. A single one of these can actually increase the outputs to 8. However, they can be strung together in a chain practically indefinitely within the limits of your code variable size. So you can use these to drive arbitrarily many LEDs or other digital output.
An analogy I've made in the past about shift registers is it's kind of like a row of buckets, and each time you engage the clock pin, you would shift one bucket forward and either fill it with a 1 or a 0. So really the length of it is infinite so long as the shift registers can accept an input, and then once they're full, then they can push out to the next register. So typically a shift register has 8 positions it can control. So
especially true for this one.
Yeah. So, and it's really a cool way to, a lot of high-speed LCD displays use methods similar to a shift register.
And these are also, as I said before, these are found in the SIK. So the principle of operation here is just basically taking a sensor reading and then driving it out to a shift register full of LEDs, which can be replicated using parts strictly in the SIK. I like using the bar graph LED because it's got a lot more pins available, or rather LEDs available to drive. And it's all soldered into a nice, neat board, so I can mount it. My original breadboard version of this, based on the SIK, wasn't really good for trying to embed into an application because, well, breadboards aren't for that; they're just for prototyping. So every time I'd move the Lunchbox, it would just completely fall to pieces.
So I notice you're just kind of going for it with the chips. Do you not have the same concern of sticking one pin down first before you move on?
And when I was rolling the pins on the ICs, it's not an exact science, so the fit is a little bit sloppy, and that sloppy fit actually allows these ICs to hang in their footprints a lot more readily than some of the other components. And you'll find that with the LED graphs also. And maybe might be helpful to actually constrain this down while I'm trying to do this.
Breaking out the helping hands.
Breaking out the helping hands. All right. There we go. Now, this does affect my height to the table, but should allow me to run down run this process a lot more rapidly.
Those are some quick joints.
Now, they're also not fully filled out.
If I remember correctly, in the past there was actually a soldering competition that SparkFun had. I believe it was at a local brewery where it was like the fastest person to put together an SIK. I think won a free beer or something.
Well, we actually did a company-wide contest to see who the fastest soldering iron in the building was. It was actually one of our testing gurus down in production.
Nice.
And at the end of the competition, the fastest customer contestant went face to face with our champion to determine who was the fastest of all time.
Nice. So to kind of get back to our temperature segment, I looked up the data sheet here, so I have it on my screen here, and it looks like this sensor is good from 2.7 to 5 volts, and it's good for -40 to +125 C. So it's got a pretty good temperature range, so well above boiling and well below freezing. But to get back to the question Josh posed, 600 C, this temperature, at that temperature, this sensor would completely melt. So, and as you can see, it comes in various packages. Obviously, the leaded version is great for prototyping, but you can get it in super small surface mount packages, and I think in some larger dip packages. So the data sheet's a great place to look. If we look through here, there's all kinds of great bits of information in here on how the temperature stability and how it reacts over voltage, the voltage output versus temperature. So. But yeah, there's all kinds of little nuggets you can find in here, and usually a lot of edge cases are kind of described in here. If there's going to be a problem, usually the data sheet's the place you want to look for to find where it's gonna hang up on you. So.
Cool, thank you, Casey. Now a little bit of a variant that I'm going to do, and I made a note of this in my wish list, is that the default case for the LED is that it comes with red, green, and yellow for sort of safe, caution, stop, general abstract. Now, because this is going to be temperature themed, I'm going to be omitting the yellow in favor of a blue. So I'll have a blue for cool, red for medium temperature, and green for medium temperature, and red for hot. So before I get those soldered in, because these are LEDs, you want to make sure to get the get your polarity correct. Now with these, there is a nice little maker's mark on the side, and that usually, very frequently, indicates that's your positive side. So, but it's always good to just double check your polarity and make sure that works. So, all right, looks like we've got a heartbeat on blue.
Now, what setting on your, I see that you're using a multimeter to test this. What setting are you actually using on your multimeter?
So on a multimeter, a good way to test LEDs is to set it to continuity, and on decent ones, it'll tone when you have continuity from one lead to the other. But the voltage that the meter puts out is actually just enough to safely drive the LED briefly. So you can see that I'm getting a little bit of an intermittent signal because it's not a great connection, but I'm just doing this to ensure that I have the correct polarity when I drop this into the board. All right, so I can confirm that the brand mark on the side is in fact on the positive side. And actually, before I get those mounted into the board, I'll drop in my electrolytic capacitor, which I probably should have done, well, actually, yeah, nowish. So, again, with the polarity, your electrolytic capacitors will have, like an LED, a long leg to indicate positive, a short leg to indicate negative, and there's also a banded negative stripe on the side. So you want to make sure to find the negative mark on your board and make sure that your polarity is correctly aligned. And then slightly tweak the lead so it holds itself in. And a little dab of solder. All right. Clip those to make sure I don't
Thanks, Mike.
hurt myself on them later. I'll try and clip the leads down so they don't go flying off into Casey's eye when I clip them.
Yeah, and sometimes, like clipping leads, you can use your handy-dandy safety glasses. Usually we just yell duck or run or...
Your safety third.
Safety third. Safety neutral now.
Risk neutral.
Risk neutral.
Yes. Okay, so as I said
we won't
before,
talk about that.
The cooler temperatures will be indicated by blue, and so I'll make sure to insert that positive side to positive side. And I'm going to put that in the lower registers, so 1 to 10.
Is there any polarity marking on the PCB itself?
Actually, there is the diode symbol that you can just follow and make sure that you're... for this particular board, the way it's laid out, the positive side faces the shift registers, and the negative side faces the resistor buses. Okay.
So the diode symbol, the arrow points to ground. So that's kind of an easy way to figure out, you know, which way to orient it based on the schematic.
And it's really good. It just indicates the direction of traditional current flow. So if you don't think about how current flows too carefully, that's also a good mnemonic.
Studying physics, I decided to just accept the double E method, and I'm okay with that.
Oh, you don't want to follow electron current flow?
No.
You go back in time and tell them they got it backwards.
Yeah.
There we go. And these guys
seems to be a little stubborn.
Can be a little bit ornery to get aligned. The manufacturing tolerances on these are, you know, good enough to put into a production run, but there are sometimes inevitably going to be headaches. A little bit of finagling and it sits nicely. And that was blue, so next I'm going to want green. These two are already going to be a pain. Okay, so those two as well. And this is the trickiest part of this entire build, is just getting all of these little pins aligned.
Steady.
Don't tell me how to solder. I'll do this any way I like. All right, if I can. Now, I find that when some of the more accessible pins are aligned and some of the harder ones are not aligned, I find it easier to try and reorient it so that the ornery ones are, or so that the easy ones are actually inaccessible, and then I can take my handy dandy SparkFun warranty voiding screwdriver and one by one adjust the ornery pins. That is a beast. And if you're into shortcuts, maybe you could also pick up a ZIF socket and solder that in place, so you can just drop the module in without any soldering or any fuss. Although, sorry. Go ahead.
Oh no, I was gonna say. So it looks like you're trying to get one side in, and then use that with some pressure to kind of straighten them out, and then slowly, almost like picking a lock.
Actually, I was about to use that exact reference. Leaving that pre-tension on there and
there it goes.
Slightly poking the tumblers like you would find in lock sport. So green is middle, and then red for the higher registers for 21 to 30. And now that I'm not in the middle, it might be a little bit easier to get at. And I'm also, I was stressing the importance of having these pins nice and aligned, but I also found that if I warp out the end pins a little bit, I can get a little a crooked line, and I can actually bring it in and bend the pin around that. So there you can see I've got all 60 of these pins aligned. The spacing between the board, or between the modules, does sort of get a little bit of skew, but that should be sufficient that I can solder that down and it'll have a good secure connection. So with this row of 60, I especially want to use my third hand here because this will go a lot more quickly if I don't have to hold the board. as I run down the line. So I'm going to do this one right-handed. And then hopefully, let's see, tin my tip there, and then hopefully I can just run this down the line. It's not as fluid of a motion as I was hoping for, but it's getting a decent connection.
So the temperature that you have your soldering iron set, are you trying to set a little higher than the melting point, or way higher, or?
You know, I never really took into consideration the melting point. When I was in production, I usually just kept mine really hot so I could get a good hot burn and then not loiter and pull away quickly so I didn't damage the board. I usually like to keep mine set at 715. Although this one's set at a cooler 650, and it seems to be doing just fine for us.
So a common tip that we tend to give to beginners at soldering is to actually lower the temperature, usually around to about 600, and that gives you a little bit more time to solder without fear of burning the board.
Sure, and it definitely works. As long as the key is to make sure that you can get your solder melted and both in contact with the pin and the pad. So the key is to basically get your pad and pins heated up to the same temperature, and then once that happens, the solder will flow freely between them.
Now, do you need to do any cleanup to the board after you're done? I notice you kind of got a little flux floating around.
Now, this since I'm not using any additional flux, only that which is in the solder itself, it's not essential. However, it's a good practice that we employ in our production methods, and I try to employ whenever I do something a little bit more serious than this. Is that I'll take it down and I'll scrub it with a little bit of deionized water and a toothbrush, and that helps to get most of the flux off. And the reason why I want to do that is because the flux is both mildly corrosive and mildly conductive. So over time, flux left on the board can cause damage to the board. It can also short traces that shouldn't be. In this case, I'm not too terribly concerned, so I'm not going to run this down to production and have the guys scrub this one off. It should just be able to run straight as built.
It looks like there's plenty of room between the connections. You know, obviously with something, you know, if you look at the Pro Mini, you know, the connections are much closer together. So, you know, solder flux bridging is a little bit more concerning.
These in our production process, these will actually get put into our Trident machine and get automated washed, just to ensure that all of that excess flux is cleared, and that's something that we employ on all of our boards. Some are a little bit more moisture sensitive, especially those with moisture sensors or things with a lot of tightly encapsulated parts, because capillary action can draw water in and be really difficult to get out. So when it powers on for the first time, you want to make sure that it's very dry, and those tightly encapsulated parts tend to hold the water, and you can actually ruin a lot of good boards that way.
Cool.
And this is there are a wide variety of side cutters available to trim these. When you're doing a lot of leads, you might want to use a larger blade, simply because it'll allow you to get a more consistent cut along them. Now again, given the nature of this project, it's the evenness of the cut is not terribly a concern, so I'm fine with these nice little compact cutters.
So to answer a quick question from online, Tony asked us, why would you use deionized water? And the simple answer is, well, so deionized water is essentially they filtered out all the minerals and salts. If you've ever lived on well water, you notice hard water stains. That's probably going to do a lot worse on a circuit board than flux. So you really want to make sure that the water that you're using to clean your boards is cleaner than the material that's already on it. So the wash machine downstairs, it actually looks like a dishwasher.
It actually kind of is a dishwasher in its functionality, and in fact we like to joke about its being an over-glorified dishwasher.
Yeah.
But it does have a lot of automated features, like for instance, it determines how clean the water is coming off of the boards by measuring the resistance of the water, because like I said, the flux is mildly conductive, so the Trident actually leverages that particular feature, characteristic of the flux to determine how ready it is to be done. Now that I've got all these clean, I want to go back and make sure that that none of these little hairs are sticking around. Nylon toothbrushes.
Hairs?
It's just the little whiskers from the trimmed leads.
So the cuttings.
Yeah. Now, on the LED, the worst that it'll do is sort of cause a bridge, and 2 LEDs will light up instead of 1. But if you have slightly more sensitive parts, or if you have high power parts, you definitely want to make sure that you don't have shorts going on your board when you power it up, because in higher power you can definitely cause a lot of damage. So that is the completed LED bar graph module. Actually, the next thing I'm going to do is to add the prototyping perf board to it. Now for this, I'm just using our 1-inch double-sided 9x9 prototyping board. And let's see, that FTDI. Okay, so
I'm like the sous chef.
see, that's the LED side. Okay, and I will solder a header into the LED bar graph. I only use 5 pins. We're not using the clear pin on the board, so I'm just using the clock latch, signal in, power and ground.
So I'll take a
Take a look at that.
Oh, see if it'll focus.
And then with the header, you can do that same tacking method.
So is there any particular reason you're not using the clear pin?
It's just that the code doesn't call for it.
Okay.
There's a software-defined canvas clear that's in the code in the library, which I employ both in the setup and at the end of the loop. So there's no need for a hardware-defined clear there.
So going back to that analogy of using the buckets on a train or a line, the clear line is essentially just emptying everything. So it's a quick way. If you load an image into, say if you ran a bunch of these together, you had a bunch of them lit up, you wanted to just clear them all real fast, instead of having to shift zeros all the way through the system, all you have to do is hit the clear line and it goes dark. So. And
the library provided for operating this actually has a software-defined clear, so you don't actually just have to send zeros. You can just say canvas.clear and it sweeps it.
Oh, nice.
So what I just did here is I removed the plastic shrouding, or the plastic binding from all of the headers that I just soldered in. The reason why I did that is because I wanted to make this as low profile as possible. Let's see.
For maximum lunching. For
maximum lunching. Now, I'm a growing boy, so I want to make sure to fit as much lunch as possible into that lunchbox. So every little 1/10 of an inch helps. And again, once I'm on the other side, same thing with the single tack.
I guess I'll try to show you what that actually looks like installed in the box. It's very cleanly done. We'll try to either get a top shot, or I'll zoom in with my nice little camera.
All right.
But you can definitely see that every little inch makes it that much smaller and much more low profile. So I notice we don't quite have a battery holder in here, but I guess that's up to the user to kind of figure out whether they want to run a 9-volt or a lithium battery. Could you run this from a lithium battery?
Because this is using the 5-volt Arduino, you can run it off of there, but you are going to have to boost that level if you run it off of a 3.7 LiPo. Okay,
so really the limiting factor is the Pro Mini here. So if you were to run it with a 3.3 volt Pro Mini, you'd be set to go?
Absolutely. And another thing that I was thinking about, this is probably a thought for a later revision of this design, is actually including in the wall mounting a place to put our hard mount 9-volt LED, or sorry, our hard mount 9-volt battery connector, and actually screwing that into the side of the sidewall of the lunchbox, so the battery is not just hanging around, bumping against lunches and possibly introducing unneeded strain into the battery clip. Another thought that I had, and this was well after we'd published the wish list, is instead of soldering the 9-volt directly into the board, to actually include the breadboard-friendly barrel jack and just go straight 9-volt to barrel jack. That also allows for a more modular design, so you don't have to straight unplug the battery. You can just pull the whole power cable.
Nice.
Also, reduced strain, which is definitely a plus.
So I have an example of what I assume is how that lunchbox actually started.
That was exactly how it looked when I got it.
So tell me a little bit more about this. Like, where'd you find this?
So for our 10th anniversary last year, we decided to get our CEO a lunchbox with his favorite lunch, goldfish, and we did some custom stickering. We actually did 2 variants of this. Actually, one was meant specifically for Nate, and says, you know, I think something to the effect of, I started this company 10 years ago and all I got was this lousy lunchbox. But the rest of us also got these stickers that just say a decade of DIY. So we did some research, found a nice, good, low-cost steel lunchbox, and we ordered a bunch of these, we ordered a bunch of stickers, and you know, for a little bit of extra SparkFun flair, I decided that I'd just spray paint mine red.
Nice. Cool. Well, I'll talk just a little bit. I'll let you kind of continue soldering about how to actually cut the window into the lunchbox. So here, there's obviously a hole that needed to be made, and I mean, this is a really nice little aluminum, or I guess a tin.
It's steel.
Steel case, and you know, there's multiple ways to cut it, of course. But let me grab my favorite tool here, which is the Dremel or rotary cutoff tool. So this uses it's just a simple motor, and it spins a little rotary disc like this, and so it's a simple little grinding wheel. And it's great going through metal, but the problem is it throws lots of sparks everywhere. And if you've ever worked on automobiles, sparks ruin the paint job. So, so a common trick that I use to kind of, let's say that this is already painted, and maybe it's like Spider-Man or something, and I really just don't want Spider-Man's head to be melted. So what I do is I'll take this masking tape here and cover up essentially the areas that might see sparks, or with these, they can kind of dance around a little bit. So if it moves side to side, you know, you're less likely to scratch up the paint job. So it's kind of a neat little trick to make sure that the finish comes out really nice. So, and of course, you know, when you're using a rotary tool, you should always have your safety glasses. These wheels, they tend, if you twist them a little bit, you'll actually shatter them, and then little pieces of wheel go everywhere, and that's no fun. So always wear your glasses, especially, you know, have your friends wear glasses. Not just you. Have your friends, their eyes are cool too, they need them, so.
Yeah, especially if you're just wearing regular glasses, there's no side protection, so if he was cutting around there and the wheel went, it could go straight into my eye.
That'd be terrible.
That would be terrible.
But you have health insurance, right?
Yeah, we've got excellent benefits here. So.
Great benefits.
So yeah, I've got the Pro Mini mounted to the board now, and I've got mounted to the headers mounted on the Pro Mini, and I've got the extra shrouding removed, and I've got that anchored down so I can just run down the line.
So it looks like you've done about the same thing that you did with the proto board, and you've just used the headers.
Exactly, and I'm just double siding the headers. Come out one side, take off the shrouding, direct contact to the board, and then solder it onto this side. It's great for that really low profile. Also, with the way that I mounted the original, you'll find that one of the bolt holes is actually partially obscured by the green proto board. And with this right flush up against with the boards right up flush against each other, you just take your drill bit and just run it through if you want to actually hard mount that down with a screw.
Okay, so you actually you went and essentially cleared that hole.
Cleared that hole, just drilled straight through it.
See if we can find that on this one.
And you'll see when you get in there, you'll see the nut hanging off of the back, sort of in the middle of the nest of wires.
Okay, cool. I'll just use this. So it looks like right here is where Evan ended up drilling through this PCB so he could get the bolt through, and then the nut. Now, do you have any concerns with this? I mean, this hardware is made of metal, and you have some circuitry, obviously that conducts. How careful do you need to be with?
With this, the parts are far enough apart where you don't have to worry too much about it. If it is a concern, there are nylon nuts available, or you can stand off the hardware a little bit better, or even do like a clear coat on the PCB just to make sure that nothing cross conducts. This circuit I've had built for a couple of years now, running it occasionally, and hasn't given me much problem.
Nice.
All right, so 3 boards are now put together, so it's time to build the sensor probe. Let's see if I can remember. It is.
And I have the data sheet.
You have the data sheet here, so don't guess. Read the data sheet. Read the manual. Make sure you know what you're doing.
And on my screen, I'll see if I can zoom in. Enhance.
So with the TO92 package, you got 3 leads, obviously. If you look at it from the bottom and call it 1, 2, 3, left to right, 1 is going to be...
It looks like 1 is VS.
Voltage, okay. So I'm going to splay these out a little bit so I got some room to work. Maybe break out the third hand again.
So, in my experience, a fun thing that I've found is working with datasheets. Sometimes they just label the pins. Some of them don't give you bottom view; they just assume that. And I've had on a number of occasions the pins essentially. What I saw was the top was actually the bottom, and then once you get your board done. It's a lot of fun trying to turn your chip pins backwards to make them fit into the socket correctly. So, but you never have those problems because you read the datasheet twice, right?
Yes. So it's, with this one, it's going to be a simple power, signal, ground. Signal in the middle. So I'll make sure to get that in place.
Now it looks like you're trying to color code your wires a little bit, or?
Yeah, I try to follow conventions as much as I can, especially when it comes to power and ground. Black for ground, and then red for 5 volts or 3 volts or whatever your low voltage DC running voltage is. And then I frequently like to use white as my first analog signal, and that's just my own convention. It doesn't really mean much.
So what do you use for your second analog signal?
Yellow.
Yellow.
However, if
Of course.
of course, if I'm doing something with a complicated serial connection, like I'm going to be utilizing SPI on the board later, I sort of let that fly out the window, and like I said, it doesn't really matter as long as you maintain consistency. Mm-hmm. So
Or document it somewhere.
And the fritzing diagrams, well, this one I think I did use. Oh no, I did use standard servo, black, white, and red. So, yeah. Next, I want to put a little bit of heat shrink on because I still have an open-ended cable here. I didn't have to put the heat shrink on first. But now,
so if you say these cables had to be heat shrunk, these leads were already connected to something. What kind of challenges would you come across?
It's frequently a challenge to just remember to put your
Just remember to have the heat sink
have the heat shrink on there before you close off the second end. Also, another challenge I frequently come across is if I put the heat shrink on too quickly after I've soldered the joint, it'll start to heat shrink before I'm ready for it to.
Yeah.
And of course, I forgot to grab.
Sometimes that's a feature, though. If you're out in the field and you want to just get the joints made real quick, you just solder and slip it right over it.
Yeah, and forgot to grab my heaterizer before we did this.
I actually have one.
Oh.
Because I am a Boy Scout.
That's some good thinking. So,
But no plug.
I can use the the soldering iron in the absence of a heat gun. I generally prefer to have some kind of hot air source.
And by studio magic, I can just throw the cable and it flies right into the outlet.
That's some NBA shots right there. Oh wait, is March Madness still a thing? Is that a?
I think so. Sports ball, right?
Did they sports ball it? Did they ball all the sports and score all the points? All right. So now that my hair is nice and pretty and perfect, I mean, now that I've got my joints all nice and sealed, I'll take a little bit of 1/4 inch. And yeah, I did I did note that I had forgotten to.
What happened with this one?
I had one size available in my shop last night when I did the test run, so
All right.
I call that economies of what's available on hand. Yeah. Then I'll just throw the 1/4 inch over the 3 wires so that the entire sensor probe is well shrouded.
So what is this extra layer for? Just
keeps the probes, or keeps the lines unified and out of the way. Like, you can still cause a lot of damage by getting things wedged in between here. Mm-hmm. So I just like to have a nice, neat little over shroud.
keeps your Cheetos out of the Cheeto dust out of the connections as well.
Rule number 1: thou shalt not Cheeto finger the character sheets.
Rules to live by.
All right. So this is another thing that is not necessary, but I like to do for an aesthetic, is to just twist when I have 2 or more cables. I'm not necessarily worried about adverse inductance or any parallel capacitance or anything like that, so I'm just going to set that through. And I'm going to take the mounting hole that's available on the perf board, and I'm actually going to just jam these. Let's see.
Yeah, I see you've done it on this one.
Yeah, and basically I use that as a small measure of strain relief, because these are all fairly stoutly fit through here. And I just need enough to reach, for the white to reach the analog 0, which is directly across here. So I can actually pull back some of that slack and have it sit a little bit more tightly on the board. As you can see on the test circuit last night, some of them are fairly tightly mounted, but towards the end it just got, I just need to get it located and installed. So there's power, or there's analog. I can pull that back a little bit. And then my power and my ground are going to be a little bit complicated. That's probably the most complicated part about this, is because you're taking the battery clip to ground and raw. However, I mean, there's 3 grounds available on the Pro Mini, but to keep it low profile, there's only 1 available on this side. So I'm going to try and get everything tied into that one. So I'll run the positive of the battery to raw, and I'll run the ground from the Pro Mini into the board, and then I can bus it to all of the other components that need ground from the board. And that way you end up not having to do these tricky little 3-way solder joints where you're trying to where you have 2 things soldered and you try to add that 3rd component, the other 2 just go their own separate ways. Each time I build one of these, it's going to be a little bit unique. So this is where the needle nose pliers come in handy. And just threading the leads into place. Okay, so I'm not going to solder those just yet because I'm going to do a lot of counter laying across each other. It just helps when working with discrete perf board. I like to cut a little bit extra length on the lead so I can fold it over and solder it into the neighboring joint.
Okay.
That way, I mean, we do have boards that have all of the holes already connected, and you just cut the ones you don't want connected. But that can be extremely tedious to try and keep track of everything, because next thing you know, half of your components are still locked in the ground plane, and that's not a good situation.
So it looks like what you're doing is you're taking the wire and using it as kind of the conductor to connect to the rest of the components. Could you just use a solder blob across that, or
Absolutely.
Are there anything?
With 0.1 inch spacing, it might be a little bit tricky to try and get to bridge unless you use an obscene amount of solder. So that's why I like using a little bit of wire. It just gives that blob a guide. Yeah. And you can see in your close-up shot that there are definitely some good healthy blobs. But I think in my experience, having the wire there helps to guide those blobs. Let's see. Oh, all right. So this is where it starts getting a little tricky, and I have to think about what I'm doing, because when I did this one, I actually ended up closing off a lot of available avenues to existing connections by not plotting out what I was doing first. So I want to make sure to get all of the connections to the signal bus and to the Arduino established first. Well, I'm going to start with the signal bus and then start braiding once I have all the wires in place, so I don't end up braiding over a vacancy. There we go. Just crook that pin over. All right.
So I notice you're using solid core wire for this. Is that just so it wants to stay in place a little bit more? Or?
Yeah, it's that single piece of metal is a lot easier to try and manipulate than a frayed mess.
Sorry, I'm stealing his tools.
How dare you?
Are you done with this?
Yes, you can fidget with it. So yeah, it's also good to keep the workspace clear of any excess debris. So otherwise, you end up.
My biggest fear, especially building robots, is you put it all together, and then you get it ready to ship it out to a competition or to an event, and then you pick it up off the table and you see screws everywhere, and there's that sudden fear of, what did I forget? Because I didn't start with this many. So yeah, I would keep your workspace clean.
All right, it's a sound lesson to heed. So I'm just referring to my fritzing now to make sure that I actually decided to color code this with the build, so I can actually refer to this when I want to know what to do next.
And is that fritzing by chance in the GitHub?
Yes, actually it is. So yeah, we've got all four major components. Well, the fritzing diagram itself is available in the 2D section of the repository. Okay. Let's see, sign, signal in, I chose that to be blue. And again, these definitions are completely arbitrary.
But you said yellow had to be.
Had to be. That is not negotiable. Actually, white.
Okay.
So like I said, I'm making this up as I go.
Aren't we all? So I'm just going to look a little bit through the SparkFun GitHub. So we have most of our products are actually anything that we build in-house. We keep the board files, the schematics, I think even like the production files. Everything's on GitHub, and as soon as we launch a product, we set the GitHub repository live. So you can download our files, take them, modify them as you will, build them yourselves, or even better, what we hope is if you find something and you think you can make it better, try to give us a pull request and say, hey, I want to help you out with this. And we do have customers that send us some really great suggestions through GitHub. So.
And that's the really great thing about open source is it allows you to stand on the shoulders of giants. Like, I'm just taking two components that I like, running them through my favorite processor, and the hard work has already been done for me, but I decided to execute it in this particular way. And if you think, okay, well, I like what you did here, but I want to tweak it here, so maybe you want to add the fixed mounted battery to the side of your lunchbox, you're welcome to go ahead and take these files and it's like, keep what you like, or keep what you like, discard what you don't, and change what you need. And it's a really great philosophy for helping to bolster innovation. Because I couldn't do any of this without standing on the shoulders of giants, as it were.
So looking back in this GitHub, there's kind of three sections that Evan's got set up here. So there's the 2D, like we were just talking about, is the fritzing diagram. And I think I goofed. I don't have fritzing on my machine, so I couldn't open it for you. But in the 3D, like we were talking before, these are the 3D models of the lunchbox, the bezel, and does it look like we also have the models of the components?
Of the circuit board, the perf board, and the Arduino. I don't think I made one of the temperature probe, but I did all of the small mounting tackle, like the latches and the handle mounts on the lunchbox itself.
Nice.
And those were all drafted originally in SolidWorks and then translated to mass consumption in STL.
Okay. So, and then if we back up one directory, we look into the firmware, and what we have is essentially the code that you'll probably be going over here shortly.
Yeah, ideally I'll be getting into that real quickly.
Nice.
It's just a question of how quickly I can get this all tied together. And I say tied. It is a very fluid, ropey mess. Let's see. Oh, looks like I just went straight across that one and then just did a top surface mount. It's not necessarily a good, clean joint, but this particular part of the assembly is fairly congested, so it makes it easier to make the other connections if I sort of cheat a little and just go straight in over the top on this guy. And that should be enough. There we go. I can probably trim off a little bit more. Come on.
So you're making great time with this. We've had some builds in the past where it's come down to the wire. So maybe we should do like a SparkFun Live Iron Chef. Like at exactly 1 hour, you have to drop all your tools.
Your secret ingredient is Big Bone Black. Ah! Yeah. Sore subject around here.
So yeah, maybe an Iron Chef would be a kind of a fun thing. So
I don't know.
Feel free to comment.
Let us know what you think.
Yeah. What do you want to see more of? More fire? Less fire? Well, there's not any fire, which is good. But we can make that happen, maybe.
Well, it is SparkFun, so Sparks is part of it. Sort of the nature of the beast. All right. Clip it there. And I did, as a time-saving measure, try to pre-clip my wires, but these are not measured quantities, so I just sort of eyeballed it, so there's going to be some post-clipping having to be done here. I was really hoping to take off a lot more jacket with that. All right. And keep that over, and thread it through. And we like to do a lot with sewable circuits, and sometimes when you're doing your perf boards like this, it can feel like sewing because just the weaving up and through the through holes.
Yeah, I definitely know that feeling. Before perf board, using perf board for building big robotic systems. There was a system that used to be called wire wrap, and essentially what you would do is you would just put the legs of all the chips through, and they'd be really long. And instead of actually trying to even create traces, you would just do like a point-to-point wiring from each component. And looking at old hardware that used wire wrap, it was incredible to see like the immense rat's nest behind it, and then you'd see little tags everywhere trying to give you a roadmap of at least where you are on the board. So I admire the people who worked on those and the people who somehow made sense of it. But man, if something's wrong on that, I don't even know how you keep up.
We've seen some of your wire wrap work, and it's poetry. Stop! You're embarrassing me.
Yeah. So I'll see. So I looked up just a quick little picture to give you an idea of what wire wrap looks like. So, and kind of how crazy things can get very quickly. So.
Did you just get a sudden craving for spaghetti dinner?
No.
Okay. No.
Not at all.
All right. So it looks like I've got my most of my guys connected for the SPI bus to the there we go.
I noticed your Pro Mini isn't blue.
Oh yeah. So a little bit while ago, we had a nice little Christmas sale where we did a variant on the Pro Minis. We called the Pro Mini Christmas Candy. And for those who were lucky enough to get one, I actually managed to get my hands on one because I felt the need to place an order for on that in that time. And then last week when we had the great big run on Arduinos, it suddenly occurred to me that I don't have a Pro Mini set aside for this, and I'm not going to get one. And then it occurred to me, wait, don't I have that Pro Mini Candy that I've been waiting to use on a project? So this ended up working out for me fairly well.
Nice.
Okay, so analog.
Yeah, the Arduinos are kind of in short supply around here, and a small black market within the office has kind of formed of people trying to find these things, because as soon as we make them, they're going out the door. So anybody who's trying to build projects around the shop lately are pretty hard to find them. So, but thanks for the exercise.
And lately, it's also been providing a nice little challenge in tech support, because this is, the Arduino is our #1 starter board. So I've been trying to recommend around that, and maybe pushing people to the Leonardo or the 32U4 based ones or the Mega. Although sometimes it's a little bit more of a board than you need. But hopefully we'll be back up with the 328 based Arduinos really soon, because yeah, I know I'm jonesing for it.
Yeah.
Okay.
I need my boards.
I need my boards.
So.
All right.
So it looks like you only have a few more connections to make.
Well, I do still have my power and ground junctions, and then I got to add my my power inlet battery clip.
Can I help you with that?
Yeah, if you want to trim that down.
I'm helping.
Helping.
I'm going to try to mimic exactly what you did here.
All right. Yeah. All lengths are approximate, so.
Oh, I have a set of calipers here.
So okay, we want to make sure to get this straight set to aerospace standards.
Okay. Rocket science here, people. Rocket science. So I'm gonna make them a little longer just in case I do it wrong.
All right. It's always better to have too much than not enough.
So, and with stripping wires, because I don't exactly know what gauge this is, and my biggest fear is if I start with the smallest, then you end up like ripping off most of the wire, and you're left with two little strands just hanging on for dear life. So I tend to start the biggest with the biggest gauge, and then work my way down if it doesn't work. So.
And it does occur to me that I'm going to need a little bit more of each of the red and black to establish these junctions. All right.
I hope that's right.
Terrible. Do it again.
Yes, chef.
I know what that means. So, I've got this one, and these guys are going to be subordinate to VCC. That's the regulated 5-volt line. And I'm only going to have one line. That's going to be the positive line on the battery cable itself, going to raw.
Okay. So I see here on the, let me get into some better light here. So it looks like this, I need a stick. This little power lead, so this is coming from the battery. So this is using the regulator on the Pro Mini itself to essentially bring it down to what, 5 volts?
Mm-hmm. Yeah, regulates the unpredictable or semi-predictable output of that 9-volt battery into a nice, clean, filtered 5-volt signal that the microcontroller and the display and the sensor can all use. Because the sensor is an analog sensor, it's listening for changes in voltage. So if its baseline power signal isn't constant, it's going to affect the accuracy of the readings.
So an analog, measuring analog voltage, you obviously have to have something to reference against. The code in your library, are you using an external reference or an internal, or?
No, I'm just using the 5-volt the 5-volt baseline for the Arduino as the reference.
Okay.
Generally, the AREF and VCC are not AREF. Is that right?
Yeah, there's a reference line.
The AREF are pretty closely tied, so there's not really much special consideration that has to be done there.
Yeah. This is a pretty stable system. I mean, The current flow is pretty predictable. Something like a robot.
Something with a lot of inductive load.
When you have a lot of motors, throwing currents around, you can see the battery voltage dip really quick, or you can see noise. And so typically, what you'll do is you'll use the analog reference line with a nice big capacitor on there, and it's a really great way to have some sort of nice rock solid voltage to measure against. And essentially that's really all the microcontroller is doing, is it's taking the voltage that's coming in, it looks at the voltage that it's referenced at, and it's giving a percentage of how close am I to the reference voltage.
And when we go into the code, you'll actually see the math that's going on for the expected values. Because it's because the Arduino utilizes a 10-bit analog to digital converter, you're going to have to basically divide that into, or at least scale that against the millivolt increments that that will indicate the differences in temperature. I don't remember off the top of my head, but it should say in the code what the actual translation is. I think is it about 5 millivolts per degree?
Here, I'll try to look that up for you.
Each reading, each tick is about 5 millivolts. So that does the that just does the voltage conversion. The temperature conversion actually comes up a little bit higher in the loop. Actually, the first function within the loop. We'll get to that here in just a second. Ideally, I'd
getting ahead of myself here.
Patience, young Padawan. All right. So each time I do these power and ground buses, it gets a little bit cleaner. And that's just sort of a general practice makes perfect kind of thing. Although only perfect practice makes perfect. The rest is just refinement. Now, come here. Now, hopefully that's still tinned enough. You can just sort of blob that on there sloppily, hold it in place, get some fresh on there.
So I see that you're just blobbing kind of over.
Just blobbing over the wires. The wire acts as a guide, but the blob and the wire together provide the. Come on. And I made that nice little rookie mistake where you actually solder the solder to the joint.
Oh.
All right. So ground is now bust. Power is now bust.
Now, a fun thing I've done in the past is I've actually, to make like a ground bus with the perf board, is I've used just long lengths of stripped solid wire. And it's kind of nice to be able to, with more complex assemblies, you can kind of make a big ground bus that you can just tie into at points. But the rookie mistake that I made there was I thought that the solid wire was the solder and the wire was the actual solder was the wire. So that's good times. Hot.
And actually, I frequently find myself employing that very technique as well. Although, as a little bit of a wire-saving measure, I'll frequently use the clipped leads off of the components. LEDs are really great. They have that nice, solid, thick, square lead. You can bend and shape into any good ground traces you want. Some of my earlier work typically used just LEDs or LED legs as the ground bus. And let's see, get that into here. That might be enough. I'm actually going to have to strip off just a little bit more, so I can make it over to the next. What did you gauge that at?
I don't remember. It was the third one up.
Okay.
Yeah.
There we go. Just a little bit more. There we go. And actually, I think I'm going to go ahead and tin that while I've got it out.
Now that's because the battery leads they're stranded wire.
That's correct.
So I see that you're just kind of tinning the end.
Yeah, and that just keeps it from becoming a frayed mess. and then I can get that through and basically bend it around as if it was a solid core wire. And
Nice.
just fold that down. Now I've actually also made a rookie mistake with the stranded wire, where I will think to tin my lead after I've put solder, or I'll think to tin the lead after it's already been frayed, so I'll end up with a nice permanent fray.
So
that you just can't use. So at that point, you just got to clip off the termination.
Just
and
start over.
I'll just touch that with the tin line here. All right, and then give it some fresh solder. Now the smoke coming off of the solder, that's just the flux burning off, and a little bit won't hurt you, but if you're doing some serious quantity, like for production, you'll want to have a good ventilation system. For just building this, I think we'll be fine. Although, you know, if
hopefully
40 years from now we both get cancer, you know, I blame it on the radiation in Colorado. All right, so that is a board.
Wow,
and
we're done.
Yeah.
Almost.
So before we started, I actually took the liberty of programming my Pro Mini Candy with my trusty dusty 5-volt FTDI with header claws available. So I didn't actually solder the headers into place, and I can just hook it up. Let's see, match my colors, green to green, black to black, and then with a little bit of pressure against the side of it,
shall I?
I've actually got it, and I can actually rest it here. Doesn't look like we're quite good there. So I'm gonna try. I'm actually since this should be running the code. We can actually, I made a point to drop in the serial debug into the line, so I can just, okay, looks like we're reading about 68, 69 degrees in here. And yeah, I'm definitely getting a good solid reading off of the temperature sensor. So there's clearly something's not kosher with my connection here. I can double check it against both the fritzing and and my circuit from last night to make sure that all my connections are correct. So let's see. Green is now. Oh, yeah. So let's see. Latch 10 is on yellow. Okay. Signal in is blue and on 11. Signal in, blue on 11. And then clock, that's green on pin 13. Okay.
Do you by chance need to power the LEDs from the battery?
Actually no, I was powering the LEDs from the 5-volt line. Let's see, 5 volts. 5 volts to the red line. Okay. 5 volts to VCC. Okay, so that's, what do you got?
So it looks like, yeah, you got your power bus.
And it's also a good idea, and I kind of skipped over that. It would have been a good idea before actually committing the bar graph to the rest of this board if I had actually just done a straight dry test of the bar graph to make sure that I'd put it together correctly. So let's see here. All of my positives facing this way.
So
all of my notches.
Maybe I'll take a look at this, and would you want to start going over the code on?
Absolutely.
On the turkey in the oven?
So
the old turkey in the oven trick.
I can hook up power to this guy, and you can see that the pipper here is moving around a little bit wildly. And I think it's just because I don't have a good clean signal like we'd talked about. But yeah, when I let go, there's definitely a response. And so if we want to switch to the code, I can go over what's going on in here. Now I tried to make sure that I've commented everything as good as I can, just to make sure that it's readable as possible. So we'll start out at the beginning, before in the head matter before the setup. We've got our inclusions and declarations. So we're going to include the SFE bargraph.h. That's the library that helps drive the bar graph itself. And we're also using the SPI.h because we're actually going to be using the SPI on the Pro Mini to drive it. So for the variables, I'm calling the SFE bar graph object thermometer for some reason that escapes me right now. And I've got 3 constant integers that I've set. The number of bar graphs, 1. The latch pin, which is 10, which is not necessarily, which isn't necessary to explicitly invoke. The library assumes that you're going to use 10. You can use some other latch pin, but if you don't say something, it'll assume that you want 10. And then the temperature pin, that's 0. That's my analog 0. And you can say A0 or you can just say 0. Arduino knows what you're talking about. And then the one variable in here is pipper. That's what I named the character that's actually the display pixel. So in the setup, we're going to begin, just like you would on a serial, we're going to begin the bar graph object, expressly defining latch pin as 10, and expressly defining the number of bar graphs as 1. Also, for serial debugging, we're going to bring up the serial function at 9600, standard Arduino value. And then just to make sure when we first power up that there's not any extraneous signal getting sent, we're going to clear the screen using thermometer.clear. So that's just the clear function in the bar graph object. So for the loop, we only have about 6 commands that we're going to invoke. The first one, we're going to establish a floating variable for the temperature, and that's just the math that defines the relationship between the temperature output of the pin and the actual, let's see, the temperature output or the voltage output of the pin and the actual ambient temperature. And to do that, there's a 500 millivolt offset. Then we're going to multiply that times 100, and then that will output to a Celsius temperature reading. Now, if you live in America and you like your Fahrenheit degrees and your feet and your miles, you can then multiply that value times 1.8 and throw on a little 32-degree bias to make it correct. Let's see. For the pipper function, we're just going to map the output from the temperature from 20 to 110, and those are the values that I chose as the boundary values. It's going to be 20 positive and 110 degrees positive, and that's just so that the 30 volt the 30 LEDs give a nice little 3-degree increment per dot. And then
rarely we'll be measuring boiling temperature inside the box.
So I decided to cap it at 110. If your lunch is over 110 degrees, it's probably a hot lunch and still fine to eat.
Or it was a cold lunch, not fine.
Yeah, if you left your lunchbox in your truck in the sun and it's reading 110,
and it's a tuna fish sandwich.
Oh, if it's tuna, it's fine. But anyway, but yeah, you're probably going to want to chuck it out if it's been sitting in there. Let's see. So the next line is just the serial print line for temperature. That's on the serial debug, just so we can see, like when I brought it up here before, I could see that the thermometer is actually working. And then the next 3 lines are just the commands to drive the display. So we're going to clear it again, and then paint. Pipper is the value that we're assigning. We're going to paint that value high, and then send that data frame to the LED bar graph. And then finally we'll wait 50 milliseconds and then do the whole thing over. Now at the very bottom we do have a voltage translation, and basically what that does is it converts the 10-bit analog to digital conversion into what we're finding for a voltage output, because the data sheet will tell us how many millivolts per degree we can expect. The data sheet doesn't know, what size of an analog to digital converter you're using. So the Arduino uses a 10-bit, so we want to divide that value into 1024 units, and that translates to a little bit less than 5 millivolts per tick on the ADC, and that is the code.
Nice.
But I did realize that I had encountered some problems with expressly defining the latch pin. So I'm going to go ahead and modify my code in my IDE here and recompile that.
Would you like to try to reload the code on that one, see if it wakes it up?
Yeah, and I think I might have a grounding issue with this one because it's just my hand in proximity is throwing off the reading. So
your personality is just electric.
My personality is something. So that compiled cleanly after making the edit, so I'm going to go ahead and lock this in here and upload the code, and we'll cross our fingers.
Something's happening.
Well, I can at least talk to the display, and done uploading.
Hey!
So apparently the expressly defined latch pin was the issue, so we'll go ahead and take that out, and yeah, it's a thermometer. From here on out, it's just a matter of hardware mounting into your favorite lunchbox or other snack enclosure.
Excellent. So yeah, to mount this in there, I assume we talked a little bit about using a Dremel to cut it out. So, obviously if your lunchbox is made of plastic, you could probably use a little coping saw, or you could use a Dremel as well.
Or a hot soldering iron if precision isn't your thing.
That might be smelly.
Make sure to do it in a well-ventilated area.
So this little plastic piece here, did you just cut this out?
Yeah, this bezel here, I actually made on the. I drew that up in Adobe Illustrator and then printed that on our Epilog Helix laser cutter.
Okay.
Now there's a little bit of a crack in the bezel, and that is just because of an error that I'd made when I drilled the hole pattern into the lunchbox itself. It might be a little bit of a nice practice if you're not really good with precision to tab your screw hole so it's slotted a little bit. This one, the screws were a little bit closer together, and acrylic, being as brittle as it is, when it doesn't bend, it likes to crack. So So I ended up with a nice little bite there. If I had it to do over again, I'd probably just widen the holes on the lunchbox itself.
Awesome. Well, it looks like it's working. That's good. That's good. So yeah, thanks for showing this to us. If you guys have any comments, questions, feel free to throw them on the YouTube. Feel free to watch this later. Show your friends. The wish list is in the description, and the code is on GitHub. And you're going to push these new changes, right?
Actually, this change should be already live. When I originally published the value, I remember taking out the latch pin, and I was a little surprised when I encountered it in my IDE.
Okay.
So the live version should have that latch pin implicitly defined. So no 10, it just assumes 10, and that should be good to go.
Excellent. Well, thanks for showing this to us, and. Everybody at home, tune in next time for our next SparkFun Live.
And as always, if you have any questions and it's after the fact, feel free to send them to techsupport@sparkfun.com, and one of our talented tech support operators will do their best to answer you in a timely fashion. So thanks for tuning in.
Yep.
This is Evan.
I'm Casey.
Thanks for watching.